have no idea, you know, if they're going to have replacement or what.
Okay. So I want to thank you for coming to Space Place tonight. It's the second Tuesday of the month, so we have a guest presentation tonight. This is one that I've been looking forward to for a long time. It's a fascinating project that we're going to hear about. Our speaker tonight is Paolo Desiati, and he's here with his collaborator, Elena Dongia. Oh, she's not speaking. She'll be here for questions afterwards. Paolo has been working with IceCube and WIPAC for quite a few years, so doing particle physics, which is intimately connected with this project here. And before Madison, Paolo worked in Germany, also on WIPAC, or also on IceCube in Germany, and before that in Rome. So is originally from Florence. Paolo tonight is going to tell us about how we can shield astronauts from cosmic radiation with a device that they're calling Crew HaT. So join me in welcoming Paolo tonight.
Thank you. Thank you for the opportunity, and thank you everybody for being here tonight. So yes, my name is Paolo Desiati. I work at the Wisconsin IceCube Particle Astrophysics Center here at UW. And this is a project in collaboration with Elena Dongia, an astronomy professor here at UW-Madison. So this is about space, right? And then you know that since the Apollo mission, no human has been on the moon. Different instrumentation has been landed there, we know that, but not people. So the Artemis NASA project is aiming to do this again, to bring humans to the moon, but also to build a space station, this is the current program, around the moon, and start to install the future grounds for a space station. The long term is in fact going back to space and then bring people to Mars, which is the next frontier for the next couple of decades. So in fact, this is the long-term program that NASA has right now, eventually to upgrade the space technology for very long journeys to one of the near planets that has an atmosphere like us. It has a lot of similarities with Earth. In fact, Mars is the most studied planet of the entire solar system. We have rovers roaming on the surface in different locations. We have satellites taking pictures and various data from the orbit. We know a lot about Mars. We know that it might have been similar to Earth a long time ago, and somehow the destiny of the planet has been changed compared to our planet. So that's scientifically extremely interesting, and this is there is a plan to bring humans to this very faraway planet, and with all the risks that encompasses. So I'm going to describe you what these risks and harmful effects of space can happen to humans and how we can mitigate that. So going to space, apart from this beautiful Fantastic Four comic, that's how the Human Torch came to be, is about cosmic rays. But in reality, the things that's a little bit more mundane, there are various risks of having humans in open space. Here on Earth we are protected, and I will explain you how. But once we go outside of Earth, we are subjected to all sorts of radiation emitted by the sun, for example, which is a very intense source of heat, but also various kinds of radiation. And there are also other sources of radiations, for example, particles trapped in magnetic fields generated by planets, for example, around the Earth, or around other planets of the solar system. And there are also more mysterious sources of radiation. Galactic cosmic rays is a stream of energetic particles emitted within the galaxy, traveling through space, and eventually penetrating our solar system. So we have to protect astronauts from all these sources of radiation to avoid long-term risk of, that can affect the health of personnel. So, but what is space radiation? Let me tell you a little bit more about it. Everybody knows the sun. We never see this way, of course, because we can even look at it, so intense it is. But basically, the sun is a gigantic mass ball of plasma, and then this plasma produces heat, and light is the source of heat that gives us life and makes Earth what it is today. But it's also this incredibly dynamic system where the plasma that forms the sun is continuously in motion, and there are a lot of incredible, powerful explosions called solar flare at the surface of the sun, emitting a huge amount of energy, and with it a lot of particles like protons, electrons, heliums, and so forth that stream through space. And the particularly powerful explosions are called corona mass ejection, or CME. These are events that are upscale solar flare, and in that case, a big chunk of the plasma that composes the sun is actually ejected into space. And it can be so massive, it can propagate through the entire solar system, and when it hits Earth, it produces the beautiful auroras. I think you must have seen a few months ago the aurora, even in Madison, which is pretty rare. Usually we can see only close to the pole. So that's a very normal behavior of the sun, but this kind of activity may pose some risks if you are open just in space. So space weather studies exactly all this phenomenology. Space weather has a scientific scope, which is understanding the dynamics of the sun, how all the protuberances and energy emission from the sun work, why they happen, and how they develop. But it has also a very practical use. Space weather helps us understand and forecast when this corona mass ejection propagate towards Earth in order to protect all our technological assets around the planet. Satellites that can be fried, that can be damaged by this intense particle propagation. Well, as you can see here represented, Earth is actually protected by a very wide, large magnetic field. This magnetic field has the capacity to stop a lot of these particles, flux coming from the sun, not all of it. In fact, the auroras are caused by some of these particles streaming through this line, going towards the pole, and we can see these beautiful green and orange and pink lights. And a lot of these particles are actually bent away. So most of the satellites, for example, the International Space Stations, are well within the magnetic field, so they're partially protected. There is this mitigation from all this harmful radiation coming from the sun. But the moon is outside. So already if you want to send humans to the moon, we have to be careful to protect them from these sporadic events. In fact, people have already been on the moon, and somehow in the late 60s. And we know now, and I think they knew already at that time, astronauts have been very lucky that they could walk on the moon for a couple of days or 3 days with the sun emitted none of these events. No corona mass ejection, no significant flare. So they were not subjected to this intense particle or radiation emission. So they were lucky. If such an event had occurred, I believe they should have, they would have needed to return back to Earth, and perhaps they might have had some health issues. That never happened. But since in the future we are thinking to have human presence on the moon for an extended amount of time, obviously we have to think about how to protect people. So the sun is here, the Earth with a magnetic field. There's another source of space radiation which is more mysterious, and it's coming from outside of our solar system. This is a collectively called galactic cosmic rays. Galactic cosmic rays are particles like we know on Earth, protons, hydrogen, helium, carbon, nitrogen, everything we know already, which is emitted by, for example, explosion in the galaxy called supernova, which is the last phase of a life cycle of a star. A star at the end of the life explodes and emits all the material it's composed of through space. It accelerates it to extremely high energy, and this particle propagates through space, eventually enters into our solar system, and they hit Earth and all the planets. We also know the sun has a cycle. The rate at which solar flare, corona mass ejection exists it goes through high and low. So you can see these yellow curves. The number of sunspots is high, and we call it maximum of the solar cycle. And when the cycle is the number is low, we call it minimum. This happens every 11 years. And so galactic cosmic rays coming from the outside are slightly decreased in intensity during the solar maximum, because you can imagine the sun during the maximum emits a lot of radiation and push away these particles coming from the outside. And so the cosmic rays coming from outside are modulated by the presence of the sun, but it's still a pretty much constant flux of very high energy particles that are harmful to humans. If we live at the surface of the Earth, like all of us basically do, we are basically protected by all this space radiation, not only because there is this magnetic field that protects us, but because we have an atmosphere. So all these cosmic rays coming from space, when they hit the atmosphere from the top, they collide with air molecule, they disintegrate, they fragment, and all these secondary particles produced, they diffuse and dilute in the atmosphere, and only very few debris of this radiation hits the surface. So we are really protected, but as you can imagine, the higher we go, the less protected we are. In fact, people living in the International Space Station, they are subjected to almost 250, 300 times more radiation than we have each day on Earth. So, and the higher you are at the moon is even 700 more. So when we start to venture outside of space for a prolonged time, we have to make sure that all these effects of radiations are mitigated. But what does actually happen to human when these space radiation hit? There is a physics process that is called ionization. This is actually relatively simple. Whatever source of radiation it is, it can be like a very energetic photon, like light, but so energetic that we cannot see with our eyes. It can be an electron. An electron is a very tiny little particle that is in any circuitry of our electronics. It produces currents, and it's around atoms. Or it can be a neutron, which is one of the fundamental particles that form the nuclei of atoms. Or it can be what traditionally is called alpha particle, which is basically the nucleus of a helium atom. These are different kind of radiation particles that have different effects, but they all do pretty much the same. They can cross and traverse through any kind of material to different degrees. Every time they do that, they lose a little bit of their energy, which is, so they deposit some of their energy into the material. But when the energy of this particle is particularly high, they can lose energy by kicking electrons out of all the atoms inside this material. This is called ionization. So not only these particles passing through matter, even us, they lose energy, but they kick out these electrons from atoms, creating some electric currents. All these can have chemical effects. It can change the chemical bound of different molecules, and it can create some damage in biological tissues that doctors, medicine, or biologists are studying very carefully. I like the graphics. This represents the what happens to. So what is the radiation that a typical Australian citizen, in this case, absorb during 1 year living in Australia? This is very similar in different parts of the world. Some of the places on Earth are a little bit more radioactive than others. Radioactivity is everywhere. Natural radioactivity comes from all biological, like soil and plants. It comes from rocks. Well, a little bit comes from cosmic rays. As I said before, some of the debris of cosmic rays managed to arrive down here. It comes from part chemical compound that are in our body, like potassium-40. It comes from some different radioactive material. This is a very low-level radioactivity that we grew up with. We have been evolved in this. Nowadays, since we live in a technological society, we also have, in average, apparently Australian citizens absorb a little bit of a value of radioactivity from medical treatments. So usually the quantity of radiation exposure is measured in some unit that here is called millisievert. What this is just a number that tells you the higher this number, the more people absorb more radiation, and the higher this number, the higher is the risk to have complication health issues in the future of their life. It's pretty much a probabilistic statistical assessment. It's not saying if you absorb this, you will die of that. That cannot be done. This is another table. This is about the US. Typically, if you make a chest X-rays, the quantity of radiation absorbed is 0.1 in this unit. It's just this is just the calibration millisievert. So this is tells you that in average in the US, all sources, natural radioactivity, artificial radioactivity, we absorb every year only 6 millisievert, 60 times an X-ray. It's a very small amount of radioactivity. That's, it's absolutely irrelevant from a health point of view. Things become a little bit interesting if people live, for example, 6 months on the International Space Station, which orbits around the Earth, still within the Earth magnetic field, but more exposed to space. This is a little bit like a 50 or sometimes high, a little bit high, radiation absorbed in average by people living on the surface. But it becomes really more compelling if you think about a mission to Mars lasting 3 years. 6 months to travel to Mars, 2 years stay in Mars and build the first, let's say, human station, and 6 months to come back. In total, this is approximately 1,500 millisievert of radiation. What does that mean? It doesn't mean that anybody dies. Absolutely not. They can come back. They can have their normal life. But NASA has established that 600 is the number that corresponds to the career limit for astronauts. So NASA will never send anybody to Mars if we don't mitigate this amount. 600 millisievert for NASA means that people are still very healthy, astronauts, but later in life they have a higher chance than us from here to develop some diseases like cardiovascular disease or brain damage, all these sort of things. So that's just hopefully I gave you an idea of the scale of radiation. Here we are not talking about when Chernobyl exploded and people absorbed 300,000 millisievert every single hour. That's a different kind of scale of radiation. Here we are talking about a very low radiation exposure in a very long time, and so the risk is probabilistically determined and not very clear. So one way to protect astronauts is to add some layer of material on spacecraft or even their clothing that protect people from radiation from particles coming from the outside. So you have different kind of radiation that I showed you before. They have different penetration power. Some of them are more penetrating, some of them are less penetrating. The more penetrating radiation goes through very thick layers of everything, lead, water. So you need a very large thickness of very heavy material to stop them. So obviously you will never be able to stop them, but you can reduce their flux, their intensity. Another problem of passive shielding is exactly that when a cosmic ray particle, for example, enters into the aluminum material of a spacecraft, not only collides with the material, losing energy and ionizing the aluminum, but it fragments into smaller debris. And some of these debris, for example, neutrons, which do not exist in space as free cosmic rays. This is the energy distribution of cosmic rays in space. After these cosmic rays particle cross 3 inches of aluminum, they look very different low energy. There's a much higher flux of low energy particles, including neutrons, which are really nasty and are very hard to stop. So paradoxically, if you add some layer around astronauts, you risk to pollute them even more with debris of the particles produced by the impact with the protection that we want to put. So what if we imitate nature? I told you earlier that Earth has a magnetic field. Magnetic fields are generated by very intense currents happening under our feet. There's a molten core of metallic, like iron, very hot and liquid inside the Earth. And because of the Earth's rotation, all these vortices are produced. I don't know if you know exactly how the magnetic field is produced, but there is this dynamo phenomenology where the rotation of the Earth produces these vortices of currents, electric currents, that create the magnetic field. And a magnetic field around the Earth, as I told you earlier, creates a kind of a shield of a planet where particles coming from space are diverted around it and go past it. At least most of it, most of them, not all of them, but a lot. So what if we artificially generate a magnetic field by taking a conductor, like a metallic material, and having electric current propagating through it? We can generate magnetic field. Magnetic fields are everywhere in our technology. So we know how to do that. And we can imitate nature by saying, what if I generate a magnetic field in a way that I put it around a spacecraft and I protect the astronauts exactly the same way as Earth is protected by space radiation. So all these particles come from space, approach the planet or the spacecraft, and then the magnetic field push this particle back. People have tried. There are different designs of shielding, magnetic shielding, which is called active magnetic shielding. In this case, these are called. Oh, by the way, this is like a donut-shaped magnetic field or torus. This is in a way that the magnetic field is limited, is encased inside this kind of a donut. And the donut shape or torus has been used of many different concepts. Inside is the habitat of astronauts, or this a space station habitat, or a space craft traveling through space. One idea is to put all these massive torus of donuts around it, where the magnetic field is contained inside here, and particles from space can penetrate this and be diverted back because of the magnetic field. The problem with this massive mechanical structure is that they can be very heavy, from 100 tons to 300 tons. That's really not operationally possible, because bigger masses in space means a lot of fuel to move them, a lot of fuel to launch them from Earth. So it's a really big problem. So some of the concept early on in the year 2000 was, what if instead of a closed structure, I have an open structure like this, where you have the magnetic field that instead of being confined inside a defined volume, is just open into space. These structures are very light, relatively speaking, of course. This is still very heavy. They are lighter, but the magnetic field, the question is, can the magnetic field be sufficient to protect astronauts that eventually would live in this capsule here? So there are different concepts here. This is just an illustration of what happens to, for example, protons entering one of the systems. There is an intense magnetic field inside here. They are diverted back. And these are other visual concepts. The spacecraft is inside here. And this is an idea of an open magnetic field, where the magnetic field is outside, so particles coming from the side would, at least some of them, be diverted back. And the astronaut habitat will be somewhere in the middle here. So what we did, we said, what if you come up with an idea of an open magnetic field that has a shape that you can shape magnetic fields the way you want, as long as you create your artificial magnetic field in a way that we think is smart. So you know that magnetic fields have a direction, have a polarity. If you have two magnets, in one direction they attract each other, in the other they repel. That's because there's a directionality. So what if you take a bunch of magnets and then you arrange them in an array like this, where the polarity rotates? This goes to the left, to the right, bottom, right, left, up, etc. So there is rotational polarization. This is called Halbach array, and what it does, it produces basically no magnetic field on one side and all the magnetic field on the other side. That's used, for example, in your refrigerator, flexible magnets. If you try to attach the magnet on the other side, usually it does not, because it's only on one side. Or in technology, in magnetic levitation, like very fast trains in China or Germany, whatever, where the magnetic field is on one side, then there is another structure that creates another magnetic field that creates this levitation, and then your train can go as fast as you want with no friction. So what if you take this and you rotate into a donut shape? Then we basically can imagine a magnetic field structure that has no magnetic field inside, but only in the most interesting part of space, which is outside, where radiation would try to penetrate. That's what we did. Instead of magnets, we use big coils of conductors in a circular shape. We let electric currents rotate in one direction to produce magnetic field with specific polarization that rotates. You see there's a rotation in here. So in that case, the magnetic field is mostly concentrated in this area on the outside, but not in the inside. Blue means small magnetic field, and here it means higher. And then, of course, when you go far away, the magnetic field tends to degrade. So that's a rendering of the active magnetic shielding we came up with. This is actually made by very smart and intelligent engineering students here at UW. And we call it HaT, which is for cosmic radiation extending wording using Hallback torus. Torus is basically just an Hallback array rotated into a ring, basically. So that's what the idea looks like. This is where the astronaut would live. This is where the magnetic field will extend outward with a very small magnetic field inside. We don't want people to live in a magnetic field, and so forth. So with Elena here, we came up with this idea, and we were awarded a NASA Innovative Advanced Concept grant from NASA called Phase 1, which means feasibility study. So Phase 1 is a little bit a small amount of money to say, okay, what they want to do with this program says, maybe it will never fly in the future, but I'm really interested to see what you guys come up with. Maybe in the future, this could become streamlined technology, but we want you to tell us if this is a promising technology. So it's a feasibility study, and we had the honor to use this possibility to use our creativity and scientific knowledge to maybe construct something that might be used around the habitat module of the future Lunar Gateway space station, which will be built around the moon, where astronauts can live more protected from space radiation. So this project goes in different phases. It's actually pretty complex, and in the short time we had to do things in different steps. One step is, okay, I understand what I want to do. Let me see if I can optimize my geometry, like the dimension, the sizes of this, and the amount of current I want to flow in these conductors here. More current means a stronger magnetic field. So what we did some study of how, once we have a magnetic field, what happens when cosmic ray particles from space get toward it. And then we iterate this with different geometrical shape of this. And here in green, you see a typical trajectory that comes from a path of a cosmic ray coming from space, doing some wiggling thing and come back into space is the green one. So that's a good one, good trajectory. That's what we want. And the red one are those particles that manage to go through the astronaut habitat. That's not good. So the optimization is I want to reduce the red paths as much as possible and maximize my green one. Once I get that, then this is the geometry I want to do, I want to use. So and then what? Well, okay, so imagine that. You have a magnetic field. What you do with this magnetic field, you want to repel all these particles that have an electric charge, positively or negatively charged, that come from space. But of course, the electric current used to produce this magnetic field is charged. It has a charge. These are electrons. These are electrically charged. So the same magnetic field produced by each coils apply the same magnetic forces to itself and to the other coils. So there are these very strong magnetic forces that will tend to dismantle the whole structures unless a smart engineer would build a very strong mechanical structure to keep all these coils together. And then, of course, the notion is that the bigger the magnetic forces, the stronger the mechanical structure has to be, which means the heavier it will be. So it's this balance between I don't want too much magnetic field, otherwise I will produce too many forces, too much stress in my structure. I need too heavy structure to keep it hold. And so it cannot be too heavy, it cannot be too weak. So this is the trick of this optimization process. How do you generate these currents? I didn't tell you that, but the magnetic field we need here are very strong. You know, if you have an MRI, you go once in a lifetime in the hospital, you have surrounded by this machine, the magnetic field is very strong. But this has to be strong for the entire trip of an astronaut. So astronauts will live around this, you know, surrounded by this extremely intense magnetic field that is meant to protect them. Obviously, you cannot use copper wire, right? If you use copper wires and you have these very intense currents, the wire will melt because of all the resistance. So there is these conductors that's called superconductors. When they are put at a very low temperature, they don't have resistance anymore, so they don't produce heat. So the magic is that at some point there is this phenomenology where currents are sufficiently low energy, they flow with no resistance. It sounds like magic, but that's a real effect. The problem is you have to go to 400 or 450 Fahrenheit below zero. So that's a big problem. You need a gigantic cryogenic refrigerator. And then there are the high temperature superconductors that work at 300 below zero. So it's 100 or 150 above the traditional one. It makes a huge difference from a technology point of view to handle this kind of superconductors. It's still a technologically kind of a niche technology for this kind of application. Perhaps in the future there will be new superconductors that work at this temperature. That would be fantastic. It would be a turnover, a completely different world to live. We are not there yet. But for the moment, we have to make sure that these superconductors work at a low temperature enough so that they can do their job. Another thing we were imagining is that, well, in the future, maybe the spacecraft can be launched with all these structures attached to it. Or maybe it can be launched separately, piece by piece, and assembled in space. Okay, whatever you do, it has its own issue. So we kind of play a little bit with the possibility to have a folded configuration where the launch mode, all the coils are attached to the spacecraft or the habitat, and once in space, this kind of a scissor lift like this would open up and put all the coils in position. And then after that's done, they can be turned on very slowly until the electric currents reach its final value. So there are different ways you can fold it. This is probably not ideal because you have this protrusion here. So other students have imagined different ways of folding everything together. So obviously, the entire mechanical structure has to be strong enough, as I said before, to counteract the magnetic forces that will tend to dismantle the entire structure. And in fact, 85% of the mass is concentrated only in the coils, right? The coils are the most complicated technologically and from an engineering point of view, the most complicated part of the entire machine. And so if you want to protect astronauts, we had to design a system, perhaps that looks like this, where we had to make sure that the weight and the mass of this object is not that big so that it becomes a viable technology for the future. Finally, once we have all this together, the right geometry, the right magnetic field, and we want to see, so what happens to a human inside a spacecraft protected by this magnetic field. So then we use a simulation toolkit called GN4 that is being developed by high energy particle physics experiments. You know, in Geneva, Switzerland, by Geneva, there's an accelerator similar to the one at Fermilab here near Chicago that accelerates particles at extremely high energy, and what they do, they smash them together and they study what happens. So they use this toolkit to simulate particles, interaction, collision, and disintegration. That's what we need. We need to calculate what happens when cosmic ray particles from space arrive and hit the spacecraft. They disintegrate, they lose their energy, they produce all these secondary particles, and all this debris pass through a body. The beauty of this toolkit is that it has also a model of a human being with all the different organ properties, so that we can calculate what happens to the human once all this radiation passes through their body. And so you remember this 6 months transit to Mars and almost 2 years, days on presence of Mars. We had this 500 millisievert absorbed radiation. We estimated that with the system that we were, we kind of designed, the radiation absorption can be reduced by 30 or 60%. Why the difference? You might remember at the beginning I said that when the sun is very, very active, there are less cosmic rays coming from space into the solar system. So because it's less, then the reduction is, with less cosmic rays and with the effect of our magnetic field, the reduction is pretty consistent. It's more than 50%. Otherwise, when the cosmic rays during the solar minimum have a little bit more flux, it's a little bit. But there is still a reduction. Of course, in the future of this development of this technology, we still have to keep an eye on the mass of how much the whole thing weighs, how can be launched into space, how can be operated for a long time without hiccups, and how can be used to transport astronauts to this long journey to Mars and back. So that's the future development. You can even imagine something like this on the Starship that maybe, who knows, will be what will bring humans to Mars. This is just a very small list of challenges that we will have to think about for the future of this concept, to make it from a concept to a more of an engineering possibility. So all this because we want to explore space. And why do we want to do that? Well, humans have always done, if you just look at the history books, humans always wanted to explore space. Every time there's a new frontier you want to go through. All this has always brought innovation and new technology in different moments of human history. That's what we are compelled to do. This is what we want to do. And then our question is there life in other planets in our solar system? Is there life in other planets outside our solar system? So it just compels us to build the technology to go there in person or to send their remote sensing technology. And here are basically us and our collaborators from engineering and physics and the medical physics department. And this is just 2 photos of the very smart students who have worked with us from the engineering department over the past 4 years. Thank you very much.